All right, we're going to be looking at the first example on the complex circuits, page 9 of the packet. So we're going to go ahead, we're going to take this circuit and we're going to solve for some stuff. So 48 volts of power is going through this, and it wants us to find the equivalent resistance, which is it just wants me to basically figure out if this was a single resistor, what would that resistor be? And it also wants me to find the current flowing through each resistor. So these problems tend to get long, so give yourself plenty of space, all right? And to kind of give you an idea of what this is going to look like, what we're going to be doing is we are going to be going this way, reducing it down to a single resistor to find the equivalent resistance. We're then going to come back this way to find the currents and voltages in each resistor. So you can imagine that you're going to have, like, down the center, you're going to have some pictures of some different circuits. Along the top, you're going to have a little work for reducing resistors, and along the bottom, you're going to be working back with Ohm's law to find the resistance and, the voltage and the current in each of those resistors. So before we get started, let's go ahead and take a sidetrack here, and remember, what are the things we're looking for? So you need a refresher on the rules. Let's refresh them quick. If you don't, just skip ahead a little bit. So when we want to reduce a circuit, we want to smoosh those parts together. The first thing you need to do is draw your circuit, identify your nodes. Your nodes are these places where you have 3 or more wires coming together. So identify those nodes. I like to just circle them in green here on the board. Step 2, you need to look for series. So yes, I say step 2 and step 3, and it is this order very much. Always look for series first, parallel second. So we're going to look for series. Series is when I have multiple resistors between nodes. So I might take this upper path and I hit 1 resistor, 2 resistors before I get to the next node. Yes, those two are in series. When I go down this path, there is only 1 resistor along that path, so that is not a series. So whenever I identify a series, I need to combine or smoosh those together. So I would take those top 2 and I need to smoosh them together into a single resistor. Whenever you smoosh, whenever you combine, you always want to go back to step 1. You want to redraw that circuit. Identify the nodes. Some of those nodes may have disappeared, and they definitely will disappear when you're doing parallel combinations. So you go back to step 2. Are there any multiple resistors along a single path? Nope. The reason I say is do step 2 again, sometimes you miss a couple. So sometimes there might be 3 resistors in series, you only saw 2 of them. So just go through that one step again. Step 3, we're looking for parallel this time. That means we're looking for multiple paths with only 1 resistor per path. And this is between nodes. So when I go from this node to this node, I can either go up, only 1 resistor on that path. I can go down, only 1 resistor on that path. In that case, those 2 are in parallel, so I need to combine or smoosh them together into a single resistor. Back to the problem. All right, now that you've came back, we know what we're looking for. So that first thing we need to do, draw our circuit and identify those nodes. So here are my 2 nodes, and what I want to look for first is I want to look for series. So I want to look for multiple resistors along the same path. So I start at this node and I go through the up path and I notice I go through 2 resistors. Multiple resistors on along one path, series. So I automatically know that these 2 are in series. I take the lower path, 2 resistors along the same path between nodes, series again. Okay, so I'm going across here and I'm doing a series. And so whenever I add resistors in series, excuse me there, you will remember that in order to add those 2 together, you're going to just add them. R1 plus R2 will give me a new resistor. Buckets. RA. Okay, so they'll give me a new resistor RA. The 2 on the bottom will have R3 plus R4 will give me a new resistor. I'll call it RB. Whenever I smoosh resistors together into a single resistor, I like to call it a letter. what that allows me to do is it kind of allows me to say the original resistors were numbers. Any resistor that has a letter, that's something that's a combination of other resistors. So let's redraw what this looks like. So we have our 48 volts up at the top. Comes down, we go along that upper path. And when we draw these, don't feel like you have to always draw it like the picture, like an angle. Okay, I'm going to draw mine as right angles. Same thing, okay? And I have that resistor along that upper path. I'm going to call it RA. And I have that resistor along the lower path. I'm going to call it RB. RA, so I'm going to do 1 plus 3. That gives me 4 ohms. And I have 7 plus 5. That's going to give me 12 ohms. And we're back to step 1. We redrew it. We need to identify our nodes. Now we're looking for series again. We still look for series first. I follow this path, only one resistor. Okay, that's not in series. Follow this path, only one resistor, no series there. Move to step 3. Step 3 says we're looking for parallel this time. So parallel would be if I have multiple paths with only one resistor per path. Is that true? Yes, so then these two are in parallel and I smoosh them together into a single resistor. And so when I do parallel, this one's that kind of funkier equation where we need to use our inverse key on our calculator. It's going to be RA inverse plus RB inverse, and then inverse that thing. That's how I'm going to get that resistor. And when I redraw that there, you'll notice I am down to just a single resistor. I've smooshed those two together into a single resistor. And I'm just going to call it R total. You could call it REQ as well. Those are equivalent. So this is the equivalent resistance of the circuit or the total resistance of the circuit. And I can do that. I can do 1/4 plus 1/12. I get 1/3, inverse 1/3, and I get 3 ohms. Oops, 48 volts. So this is the first step of all of these problems is we need to work all the way down until we get one resistor. Now we can work backwards. Really? We're only halfway done? Yes! All right, so here we go. We're on our way backwards. So on the way out, we're doing the resistance equations. On the way back, we're doing what are the things that are the same in, say, parallel, when we go backwards through parallel, or what's the same in series when I go backwards through series. So the same thing in parallel is they have the same voltage. And so this is what we talked about in that video before. Parallel has the same voltage, series has the same current. And then we'll use the resistor and say the current, because it's the same to find the voltage, or in the case of parallel, we're going to use the resistor and the voltage to find the current. Okay? So here we go. Let's work backwards. So if I need to, I can solve this total one over here. So using Ohm's law, V total equals I total times R total. So I have 48 volts equals the total current times the total resistance of 3 ohms. And so I get a total current of 16 amps. All right, let's start working backwards. So when I work backwards through parallel, they are going to have the same voltage as the voltage across the resistor they smooshed into. So they smooshed into this resistor, which has a resistance, or I'm sorry, a voltage of 48 volts. So that means both of these have 48 volts across them. Thinking back to my diagram, I start at positive 48 volts, and I take that path and I go through and I lose all 48 volts because I ended back at 0. I don't have to share that voltage with the other path. So they have the same voltage. So what you do is you set up 2 columns, one for RA, one for RB, and they are going to have the same voltage as the one before. So I'm going to take that 48 volts. All right, so for A, I have VA is going to equal IA times RA. And so they both have 48 volts. So 48 volts times the current, which I don't know, times the resistance of A, 4 ohms. And I could find the current flowing in that one. So the current in A is going to be 48 divided by 4, or 12 amps. In B, looking at B, so the voltage of B is equal to IB times RB. And so I have 48 equals IB times RB, which was 12. Figure out the current. IB is equal to 4 amps. Now, a good check. Always check yourself, you know. If I combine these two resistances, or I'm sorry, these two currents together, because we are looking at a parallel, the total current is 16 amps. It works out. So you should always check the one you didn't know going backwards. All right. So now I need to go backwards to here, and so these all have the same current. All right. So when I'm going backwards from A, it's going to be, what was it, 12 amps. And when I'm going backwards from B, it's going to be 4 amps. So what that means is that going through B, there is 4 amps of current. There's 4 amps of current in this lower branch. So that means there's going to be 4 amps of current in this whole lower branch. So that means I have 4 amps going through each one. And so they only asked me, thank goodness, to find the current in each resistor. And so now I know 4 amps, 4 amps. If I look at the upper branch, I had 12 amps, 12 amps. Now, if they wanted me to find the voltage drop for each one, I would have to do this kind of setup again. I would have to list them out. And so let's just do one just to be safe here. So let's just do R4. Because I would have, you know, R1, R2, and R3 here. But let's just do one. So these two have the same current, 4 amps. These two would have the same current of 12 amps. So for R4, I have a voltage through number 4 is equal to the current through number 4 times the resistance of number 4. So the voltage for 4 is going to be the current, which is the same as IB, which was 4 amps, times the resistance, which was 5. That gives me 20 volts. Now, without even having to worry about this, I know that in series they're going to add up to the same voltage. So 20 plus something else, the voltage for 3 should be the overall voltage of 48. So I should get 28 volts when I do that one. But all we needed to find was their currents. So there we're done. Let's have you do this next practice problem. And I'm going to give you a video next that kind of works you through it as well.